And with that, I will present our first speaker for this afternoon, and that is the automation expert, Christian Larsson, who will present how to crank your NSO to 11. Welcome, Christian.
All right, thank you. All right, hi everyone. Yeah, hope you enjoyed lunch. Welcome to this session on one of my favorite topics, really getting to the core of NSO and how you can crank your NSO up, all the way up to 11. So I got this question earlier, actually, like 11. What do you mean by 11, cranking it up to 11? Which made me feel a little bit old, to be honest. So I hope that some of you out there get it, because it's a movie reference, right? Spinal Tap. I'm not quite as old as that movie, but not by much. So in the movie, they're in the store. They're selling guitar amplifiers, I think, and there's a Marshall where the volume knob goes all the way to 11, which is where this screenshot is taken from, right? All the other ones go to 10, obviously. And there's the sales rep, and he's like talking to someone, trying to sell stuff. It's like, oh, you know what it's like? You're at a gig, you're playing, you're at max volume 10, right? Where do you go from there? Nowhere, because you're already max volume, right? But with this bad boy, this Marshall, you can do one more. You can go all the way to 11. And that's what we're going to be talking about here today. How you can do one more. How do you go to 11 with your NSO? And I think that there is quite a bit of untapped potential. The vast majority of NSO installations out there, I think they're used in quite sort of basic and rudimentary ways, and I hope that this can inspire to do more. And not only that, but by doing more with NSO will actually make your life easier, as well as your development velocity higher. I've been involved in NSO for quite some time, more than a decade by now. So I and the teams that I've been involved with have learned and discovered many things over the years, and that's what I'm here to share today. So besides this session right here, right now, we have these other two mastering service design. The first one follows just after this one, but over in Bankfack 1, I think it's called, right? Then we have the second part tomorrow at the same time. We have one before. Okay, so don't look at this one. Look at the agenda online, I suppose. Now, across these sessions, right, there are many low-level details and high-level concepts that we'll be going through, but it's also not just slides. We put together a code base that we call RESPnet, the Realistic Service Provider Network, that embodies all of these concepts, what I think of as a NSO service architecture, into actual concrete code. It's open source, it's publicly available, so you can grab it from GitHub either today or tomorrow or some other day, and we should have a link here, but it doesn't say. Okay, it's easy to think of this as a mere example, but I do really think that this is a little more, right? I think you all saw Eric up here earlier, and well, and me, I guess. So RESPnet was actually what we used as the sort of springboard or starting point for the GleSYS automation journey, right? Naturally, many things were added, many things were customized, but nonetheless, I think it was an important springboard that put many sort of foundational structure and scaffolding in place that later simplified a lot of things. So I'm Christian Larsson. I'm a consultant. I work mostly on building sort of advanced network automation systems, and I mostly focus on the design and architecture stuff. But I do like to write quite a lot of code. I enjoy that. My background is in networking. I used to be an IP and optical network architect at Tele2, a Swedish service provider, for those who don't know, before I joined Deutsche Telekom a little more than 10 years ago. I also did about 5 years in the NSO BU and the CTO team, and then later in the strategic initiatives, and also obviously now together with GleSYS, I'm helping them and do some automation. But more importantly, so I'm here representing the team in Deutsche Telekom, from where most of these ideas came from. And I think out of that team, Marco is the only other one out there somewhere. But you know, come find us in the break if you'd like to talk more. I do welcome questions, but I'm a little short on time. And since we have these mastering service design sessions later on today and tomorrow, you know, really, if you like this stuff, you know, swing by and talk, and we'll do a lot more sort of interactive session. So, a little more than 10 years ago, I got involved in a project called TerraStream. TerraStream was a project, a Deutsche Telekom project, to rethink the fixed and IP optical network. And TerraStream was a design for a new network that radically simplified a lot of things. Fewer routers, fewer protocols, fewer everything, simpler. But we're not really going to talk much about that network today. One of the aspects that was quite unique with TerraStream was that it saw the management of the network as an integral part, right? Managing the network, it wasn't an afterthought, something you'd bolt on to the side. I see a lot, right? In many cases, you have network engineers, they go out, they write a high-level design, write a low-level design, lots of device config, maybe they even buy the boxes, they put it all together, and once they're done, then they go to the systems people, and they're like, you know, hey, can you help me automate this thing, right? And a lot of the time, you find that aspects of the network design are hard to automate. And if we had instead designed the two things in tandem together, then you can design networks that are simple to automate, and through automation, they also become simpler, right? But we were to build the network and management together, and the ambition was high. We wanted a fully automatic system to manage the network, for some definition of fully automatic at least, but pretty much no humans in sort of daily operations. And this was what I got involved for. And I think it's pretty obvious that you have to fully automate things like order fulfillment, right? I mean, whatever customer orders, you got to fully automate that stuff. But there's a whole slew of other stuff. What I think of as network infrastructure, right? That needs to be automated too. We don't want people to sit there carrying out sort of daily routine work. So configuration of the internal network, that needs to be automated too. And how do we do things like capacity planning? It's a fairly high level and abstract task. I found this picture in one of my early presentations, almost 10 years ago, trying to explain sort of the automation system design for TerraStream. So like a stack of pancakes, a layered approach to automation would allow us to sort of divide and conquer a sea of complexity into smaller and more manageable units. And it goes something like this. So this example is around capacity planning, just like I was talking about, right? So on this high-level sort of intent abstraction layer, we start with an abstract intent that we want to have some specific capacity between router A and B. It should be 100 gig. And mind you, you know, this was almost 10 years ago, right? So 100 gig was actually something back then. Now I think, well, there are no slower interfaces almost. But then we go down, right? So the next layer here, at this point, we now enrich this intent with more details. Because, I mean, we can't just tell the network, like, hey, 100 gig between A and B. It doesn't work like that. We need more details in order to actually turn this into concrete configuration. So we add in stuff. We find an interface on router A. We find an interface on router B. You talk to some optical thingy and go, like, what wavelength can you give me? Which one will work for whatever we're trying to build here? You also do allocation, IP prefix, IGP metrics, stuff like this, right? And then, once you have that, then you have all that sort of detailed information, and we can move further down. And I think this is the point where NSO would come in to render this configuration into something that we can send to the device. And here we are, about 10 years later. So what would we do differently? We'd use NSO to implement not just that bottom layer of driving devices, but we'd use NSO to implement all of these layers. And that's what I want to talk more about. Now, the TerraStream project, as it was originally envisioned, ultimately didn't go into full-scale production, mostly for political reasons, not technical ones. But we did end up implementing a lot of stuff. We built a nationwide pilot in Germany, thousands of kilometers of fibers. We still run that network to this day. So it's being used for like a lot of 5G proof of concept stuff and things like that, right? But it means we have a very good sort of proving grounds for doing robust network automation. We also got involved in many other projects throughout the whole Deutsche Telekom organizations, where we're helping other teams that manage some part of their little network or doing something, right? Not little. They're managing some part of something, right? Some network devices. So we've been helping out lots of other teams. So that means by now we built quite a few network automation systems. And throughout all of them, we've consistently applied NSO, and pretty much only NSO, to build the entire stack. Most environments I've seen or heard of, they look like this, or some variation of it. There's always bound to be something workflow looking, something that sits on top of NSO that does a lot of stuff. And if we zoom out a little bit further into the wider sort of BSS and OSS landscape, we'll find that almost all the little boxes that you have here, right, they are workflow style or expect to be driven in an imperative fashion. Resource tools, there's specific API points, endpoints for create, delete, update, right? And it's not based on declarative ideas. So NSO usually lives like this, like a thin sliver along the bottom of the stack, with the primary duty of communicating to devices, acting as a bit of a device abstraction. And it is utterly alone as the only declarative tool in this sea of imperativeness. Now, NSO implements this paradigm of declarative mappings, which is vastly different and sets it apart from the majority of these other systems. And I actually think that NSO, through these declarative mapping, gives us the better tools to help us break down the complexity and provide a better structure for our whole automation system stack. So why not use NSO for more stuff here? Why not use it for everything? NSO, NSO, NSO. So that's certainly what we have been doing, and we are going to talk about why it's such a good idea. But first, we have to take a closer look at NSO to understand, declarative mappings. What am I talking about? Why are they so good? NSO 101, back to basics, right? So here's some input configuration to NSO. This, I hope you all sort of recognize the concept here. I expect there to be lots of developers in the audience. So we give some intent into NSO. And this creates a service instance inside of NSO. And this one is called IBGP neighbor because it creates an IBGP neighbor on a router. If you don't know what an IBGP neighbor is, don't worry, it's not very important. Just imagine some piece of configuration on a network device, right? So once this service is created, and NSO computes a payload, it sends it down to the device, and then ultimately we get this sort of an actual IBGP neighbor established on the device. Once we're at this point, what happens? What else is there to do? Nothing, right? Inside of NSO, the service, it now sort of just sits there. And this is perfectly natural in NSO because the service, it acts as an abstraction and it represents something in real life. Through the interface that the service exposes, its API, we can interact with the real world thing. We can affect it. It's like we have this little voodoo doll inside of NSO that makes things happen outside in the real life. And this is what being declarative means. The input to NSO is declarative configuration, and NSO effectuates these changes to the external, to the real world. We just declare what we want. If we want more IBGP neighbors, we just declare a longer list of services. And each is like its own little voodoo doll, mapping to the IBGP neighbor configuration on the router out there in the real world. And again, it's the list of neighbors, the declarative configuration that we have there, that really controls all of this. It is our intent. If we want to modify a service, so we just set those parameters on the right service instance. So in this case, we want the extra premium version of an IBGP neighbor, and so we just add it in, right? What if you want to send NSO some configuration that is already applied in NSO? Well, nothing happens, right? Because NSO realizes the input is unchanged, so there's no need to recompute any resulting configuration. So not only is declarative nice and simple, it's also efficient. And finally, what if we want to remove some instance? Well, we just remove the input configuration. We remove it from our declared list of things we want. And NSO figures out the rest. We declare that we want one less instance. And compared to pretty much any other system, this is now approaching magic. We don't have to write the code to clean up after ourselves. NSO will figure it out based on what the service once created, right? And it's of course also this mechanism that lets NSO modify existing services in various ways. So it first cleans up the old version, now we recompute something and we send out the new output, right? So NSO, it allows us to build abstraction like this with declarative configurations input in a very, very simple manner. And then it takes care of the rest. All of these tasks of cleaning up and all of that, right, is taking care for us. And this is, I think, is the true power of declarative mappings. And it's the most fundamental power in NSO. So let's just consider the timeline. I like the timeline perspective of this. So on the x-axis here, we now have time. So first, we create, we send in an intent again, right? We get a service instance, it runs, it produces some output, it pushes this down to the device where it now exists, right? Then the service instance inside of NSO, together with the actual thing out there in the real world, the IBGP neighbor, is going to exist. They're going to live side by side like this, right? Up to the point over there, where we decide to delete the service instance. So we remove this line, right? So naturally, NSO removes the corresponding changes in the network, pushes down the configuration to remove the neighbor. So I think it's an incredibly important property of these abstractions, since they give us control and they help us. They make it easier to manage the full life cycle of a service and its configuration in the network. So they have a shared lifetime, right? In a workflow-based system, or any sort of imperative system, I say workflow, but it's really the same if you write a Python script or anything like that, where it has a much more imperative sort of control flow to it, right? Instead of adding some declarative configuration, listing that we want an IBGP neighbor instance, instead we run a workflow, right? That creates the IBGP neighbor. So it creates the device configuration, it pushes it to the device, and once the IBGP neighbor has been created and the workflow is now completed, so what happens? Well, the workflow disappears, right? Because workflows, they run one time, and once they're done, they're basically consumed. There are no remains. There might be like a log, right, that records the history. We did indeed run this workflow at some point, but it isn't really persisted beyond that. There's no thing, there's no voodoo doll that you can interact with further to do something else with it, right? So if we peek inside of a workflow system, it doesn't help us understand what is out there in the network right now, right? It just doesn't have that sort of view. If I want to delete the IBGP neighbor I just created, the first problem is that there's no natural key. I think of this as IBGP neighbor number 3, right? That's what I use as the natural key in the Yang model. But when you run a workflow, it is typically assigned some monotonically increasing integer, like this was workflow 123, right? And that number doesn't really say anything. So even if we do have the number, we can't do anything with it. We can't ask the workflow engine, can you please undo these things? And this is because workflow engines tend not to treat device configuration as structured data that it knows how to reverse, right? It just thinks of it as a blob of text. So instead, we now have to run a new workflow, the delete IBGP neighbor workflow, which then gets assigned a new integer, and then it runs and it can do its thing, right? But again, those are things that we have to explicitly develop and code, right? And the same goes for if we want to modify an instance of IBGP neighbor in the network, right? Since there is no service instance to be modified inside of the workflow system, the workflow way of expressing this would instead be to have another type of workflow for modifying the service. So, I mean, if we just sort of sum this up, right, with the Yang models that we have for an IBGP neighbor with NSO, we just get this very simple, we have a single create function, right? That's all we need in NSO in order to manage all of these cases. Create, update, as well as delete, right? In workflows, you need typically separate workflows for all of these, right? Maybe you can get away to actually create this sort of more idempotent upsearch style where the create and modify could be merged in together. But again, you get no sort of system support for doing this. You're on your own, so you need to write all the logic in order to do that. So I think it basically, with workflow, that style, you just lack the sort of basic structured data approach to make this a robust foundation on which you can express your automation logic. So it's death by 1,000 workflows. And to make it worse, these are just the workflows that related directly to IBGP neighbors, right? workflows, they're intuitive to understand because us humans, we tend to describe things in sequential processes. If you're going to describe to someone how to bake a cake or how to change tires on a car, chances are that it will be along the lines of this, right? You set the oven to 220, you do this, you do that, you mix it, you knead, and stuff like that, right? And I think it's also quite telling about our capacity as humans. We have 2 arms, 2 legs, and a brain most of the time. And we typically do one thing at a time, right? Actual multitasking is not for humans. Maybe something you write on your CV, but no one actually does 2 things concurrently. Computers are different. They can switch tasks, 1 million times a second. And there are actually multiple CPU cores inside of your machine that can do things in parallel. So what happens when we apply workflows to network automation? Well, we tend to describe the process in this similar, very stepwise fashion. First, get the interface from the inventory database, then go to the IPAM, then allocate the addresses, then look up some other thing, X parameter, right? And finally, compute the configuration and configure the device, push it to the device, right? And the natural way to express these tasks when we bring them over into a workflow is through a sequence, like this, right? Do the first thing, then the second, third, and fourth. But it's really a lie. There are no dependencies between steps 1 through 3 here. They can be carried out in parallel, like this. So once they are done, then we can move on and actually configure the device, right? So I think that the allure of intuitive workflows, it misguides us. It draws us into think in the wrong way. And by doing this, we end up with something that are actually much more complex. Now, networks, they are inherently complex, so we don't need more complexity in the automation. Quite the contrary, we need tools that break down in such a way that it becomes easier to manage this. That way, we can divide and conquer the essential complexity in networks, and that's a good thing. But it gets worse. How do you combine multiple workflows? How do you add them together? I think that the natural way in which workflows compose are by running one after the other, which further sort of compounds the problems of sequential processes. And again, it doesn't really help us break down the complexity in our network. So the allure of workflows, in particular those with a graphical UI, like a visual designer, is that they are easy to use and will make anything simple to automate by virtue of being visual. Anyone can drag and drop some boxes and arrows, right? But I think that they all fail to address the actual complexity. And when you add in error handling to workflows and then you combine multiple interrelated workflows, it very quickly turns into something like this. It's a spaghetti monster with all sort of temporal coupling, which is really, really hard to figure out. It's a spaghetti monster, right? Spaghetti is delicious, but alas, it is for eating, not automating networks. So back to the declarative dream in NSO, where our structured declarative mappings in NSO instead provide the support that we need in order to build large systems. I think it allows and supports us to break down complexity and scale out our systems. And I think there's a final case to consider for the declarative services. Let's say that we have created some service instance, it produced certain device configuration that it pushed down into the network. Now what we can do is to modify the service definition itself, right? So we're going to change this to be a conceptual version 2, right? The intent stays the same. We're not changing that, but we're changing the actual service definition. In this case, we want to say, there should be a description configured for this neighbor, right? And this is very simple in NSO, right? We just modify some code, some XML template in this case, right? And now since in NSO, we have all the services instances, they're right there. It becomes very simple to just redeploy those instances and in a controlled manner push this out into the network. And again, with a workflow, we're sort of on our own, right? We have to explicitly and by ourselves figure out what are the things that we have in the network, right? How do you get a list of IBGP neighbors? And then based on that, run some certain workflow to upgrade to conceptual version 2. So, declarative mapping with abstract intent is a really powerful way of managing a network. It reduces complexity such that we can make room for the essential complexity, and we have seen how it helps manage the life cycle of individual services. And many see the benefits, which is of course why NSO is widely deployed for managing device configuration, but typically in combination with these other tools that sit on top. But why stop there, right? Why would we use this fantastic tool only to manage the very bottom layer of their stack, the device configuration? Why not use it to manage more? Yes, indeed. Why not? So in a network, we commonly need a full mesh of IBGP speaker, and that's in fact what we started configuring here. Now in the core of your network, you need an IBGP session between all your routers like this, 1 to 2, 1 to 3, and so on and so forth, right? If we have 3 routers, this is what it looks like. If we add a 4th router, it needs sessions to all the existing ones, and all the existing ones need session back to the new one, right? It quite quickly gets to a very high number of neighbors. So like for 20 routers in a full mesh, you have 380 neighbors. In a real network, this runs into the thousands, right? I don't want to manage hundreds or thousands of these manually. So back to this network, right? Here we now have the list of IBGP neighbors to create the full mesh. It would look like this. So it's just a couple of routers, and so we just end up with 12 instances, right? But remember how this quickly reaches into the 1,000. So what about if we add another abstraction layer on top? One where we focus not on individual IBGP neighbors, but on composing these into a full mesh, right? Now we just have to list the routers that are part of the full mesh, and we're all done. So this top IBGP full mesh will produce all the necessary IBGP neighbor service instances, which in turn, just like before, will configure the routers. And we can think of this new top layer as a mega voodoo doll, right? Instead of interacting with thousands of different smaller voodoo dolls of instances, right? We have a single point to manage the whole. And these are now layered abstractions, and we can see this basic idea of this concept coming together here. The elegance here also lies that as soon as there is an input, an update to the input, like if we add yet another router to the full mesh, right, everything will be automatically updated. It converges on the new intent in a correct way, right? All the existing services that have already been created, like these ones, they will stay. We don't need to touch them, but all the new ones for a conceptual 5th router here, they will need to be added, right, and they will be computed. If you construct this in more imperative terms, a script, a workflow, the naive implementation would be to recompute the entire full mesh, right? But here we get the system support from NSO to do the efficient thing. Again, it's the sort of characteristics that we get for free out of this declarative model, and that actually helps us a lot in the real world, right? And we can continue to build like this. We can add layer, we can add more services to manage the whole network, not just in concrete device configuration, but in these more abstract and high-level service configuration, right? And this layer declarative mapping approach actually help us break down the problems and provide a structured necessary to think about these problems. So these are the sort of layers that we have here, right? And configuration propagates down. In reality, even the full mesh, however convenient, is actually not a top-level CFS, right? We actually have a layer on top. So this is in the RESTnet repository that we have. In the CFS layer there, we define routers, and all the routers that have the role core on them, they are the ones, they're automatically added into the IBGP full mesh. So this is now an accurate picture of the layers in use, but we're just looking at more or less the IBGP-related services, right? There are also other services to the side of this, like a base config and lots of other stuff. But at least the layers here are drawn correctly. An advantage of using NSO to build the entire stack is that NSO builds the northbound API for us, for free, right? Based on the YAMLs of the CFS layer, it automatically renders the northbound API model-driven style. So that's very, very convenient. And as soon as you place something on top, that sort of goes away. If we tilt and rotate our diagram a bit, we get this perspective in our system. And I quite like this as a mental model of the system. So we start with the CFS intent up top, comes in through a northbound API, in this case, lists 4 routers, right? And from there, it produces output that goes down to the next layer, the intermediate layer. And those services run, produce new output that goes down, and so on and so forth, until we finally get to devices. But there is also a read side to the system, right? I mean, normally when we do work in NSO, we think a lot about configuration, it's transactions, and that's all stuff we write, and it sort of passes down. But there's a read side to the system. This starts at the bottom, where we read data from devices. This comes into a device representation inside of NSO. Our RFS services can then read from there, and they in turn can expose data of their own up to the next layer. So for example, if we support Juniper and ISXR routers, then the RFS layer can support both of these, and then when it exposes this northbound, it provides that in a vendor-neutral format, right? So on the next layer where you consume this data, we don't have to think anymore about this. Is it Juniper or is it ISXR, right? And so on it goes to the top, where you now expose this on the northbound API. So we get this complete architecture that caters both to configuration and state management, and we can get an accurate view of the current state in the network. Now, if we bring up these two next by each other, we realize that they have pretty much the exact same hierarchy, right? It's like the two facets of a service. One lives in the transactional configuration world, where strict data constraints reign supreme. And then we have the other, updated reactively, sort of rooted in real-world data, and needs to be very reactive, right? And I think that this is a particularly nice mental model and approach, because when we think of a service, the code to define the configuration that it writes and the operational state that it consumes is just next to each other, right? So they basically follow the same sort of API structure. It's very natural to consider the service as a whole. The configuration side is, by definition, always consistent internally. So if you think of at least a higher layer here, right, they're always internally consistent. We only allow writes from the outside to the very top layer, the CFS layer, and then anything else is only written by the previous layer, right? Intermediate layer, only written to by CFS. RFS, only written to by intermediate, right? So we're always internally consistent. However, on the bottom, it's a little different, because we have devices. And devices, they don't live within the confines of NSO. So we need to, they're reality, they're out there. So we need to react and adapt to devices. And while we do push configuration down, we also need to read, right? If we upgrade the software on a router, the YANG models supported might change. Or if we, replace it with some other device, then there are changes. So we need to reread these and recompute the configuration that we write down. So on the bottom here, we have effectively formed a closed loop. It's closed loop automation, yet with a declarative interface, which means that for the most part, we can encapsulate this closed loop and not expose all of its details upwards. So it simplifies and it keeps the API simple, right? We can also build other closed automation loops on different layers. And once again, I think that this service architecture, it lends itself really well to doing this, having a write and a read side. You can imagine how you build these loops, right? Yet with declarative APIs on all these levels. So you get a nice structure to support your automation work. This asynchronous behavior that you get, reacting to events, that is something that we have adopted throughout the whole system. So in RESPNet, in the work we've been doing in Deutsche Telekom, right, we are an async system, and the ramifications are significant, right? So it shifts the whole behavior of NSO. The default out-of-the-box NSO, you send in a configuration transaction. If you can't push it down to devices, it just stops, right? It aborts. It says device unreachable or something like this. We don't do this. We're in a sync system, right? So the ultimate responsibility for pushing config into the network is now in NSO. We've taken over that responsibility. So in reality, that means, send in an intent to NSO. You describe how you want the network to look like, and then NSO, we accept it sort of immediately, right? We do a bit of data validation, we accept it. But pretty much after that, we're gonna start trying to push this down into the network. The devices that we have might not even exist yet, but they will be set up, we will compute everything, and then we will push it down. And like Sisyphus relentlessly rolling his boulder up the mountain, NSO will continue to strive and try to reach this target intent. And through this, we get autonomous networking, where NSO can self-heal the network, fix the configuration, and bring it back to sort of the intended state. And I think this is a really, really big shift in how you use NSO and how you run your network. But it's possible. It's possible right here and now. and RESTnet is a demonstration of that. If all this is so good, why is no one else doing it? Well, they are. Google uses a similar approach. They call it MALT for these abstraction layers, right? And talk about data flow style, because that's, the mental model of how you pass data down is very much, data flow oriented. There are some really good talks on this, so go find them. And I think that the structure is very similar to what you get when you have deeper stacked services with, layered abstraction inside of NSO. There's also Kubernetes. I'm running out of time, so we're not going to talk much about Kubernetes. I don't think it's a very natural place to solve this, but they're very much about declarative configuration. You can build custom operators. The Google's MALT, it's closed, right? NSO is available, and it's an excellent tool to build these layered abstractions. I think that the early idea of a stack of pancakes, it was quite spot on. We didn't come to implement it exactly with the systems we originally had in mind, but I think we did something better, right? Because we applied NSO consistently to the whole stack in now numerous network automation system. We get this uniform system, it's simple to work with, and through these layered declarative mappings and the service architecture demonstrated by RESTnet, it provides a structure to attack real-world complexity. It gives us the building blocks for constructing truly composable systems. And composable systems are great. It allows composition of many smaller things into something greater, and that you can still reason about the parts as well as the whole. And it's crucial that we can reason about the system at any level, right? And I think this is really what makes large-scale systems design tractable, or just simply, simple enough to be realistic. So from this, we build correct, safe, and robust systems that are simple to modify, simple to understand and grow with. In short, delightful network automation. So we're at the end here, and I am very much out of time. I'll be moving over to Bankfack for the Mastering Service Design session. So if you're interested in all of this stuff and more, please come join me and Huras over there. All right? Thank you very much for listening.
Thank you so much.
No time for questions, I think. Or?
No time for questions, but if you have any questions, don't hesitate to talk with Christian and Huras.
Yeah. All right. Excellent. Thanks.